Hello, everyone. Tonight, we're going to explore an extreme category of objects, not because we want drama, but because the universe quietly makes things that are so large, so dense, and so elegant in their physics that even thinking about them can feel like a kind of meditation. We're talking about the biggest black holes we know, the heavyweights at the top of the mass range, the ones that live in the centers of galaxies and glow indirectly through the light of swirling matter around them. And as we go, we'll keep a gentle rhythm. We'll define what biggest means. We'll look at the most famous candidates. We'll talk about how astronomers estimate their masses from far away. We'll discuss why the record can change with new measurements. And we'll end with a quiet perspective on what these giants mean in the story of cosmic evolution. No rushing, no sharp edges, just a slow, careful walk through the dark with a flashlight made of evidence. What a black hole is, in the calmest possible terms, a black hole is not an object you can point to like a rock. It's a region of space-time where gravity becomes so strong that beyond a certain boundary, all possible paths forward led inward. That boundary is called the event horizon. The horizon is not a physical surface. It's not a wall. It's a line on the map of space-time, a point of no return. And one of the most soothing truths about black holes is that they are simple in description. In general relativity, an astrophysical black hole can be characterized mainly by mass and spin. Charge is usually negligible in nature because surrounding plasma neutralizes it quickly. So if you know the mass, you know the scale. If you know the spin, you know how the surrounding space-time twists. Everything else is detail in the environment. Gas, dust, stars, magnetic fields, jets. A black hole itself does not emit light. The event horizon is dark. When we see a black hole, we are almost always seeing matter outside it. Matter heating up as it falls. Matter being accelerated into jets. Light being bent by gravity. Black holes are invisible in the straightforward sense, but they are intensely measurable by their effects. And the biggest black holes produce some of the clearest, most dramatic effects quietly from very far away. What biggest means for a black hole? When people say the biggest black hole, they usually mean the most massive one. Mass is the primary scoreboard. Mass is what sets the characteristic size of the event horizon. And mass is what ties the black hole to the galaxy that hosts it. There is also a subtlety. Sometimes people mean biggest by horizon size, which is essentially the same as biggest by mass, because the scale grows directly with mass. For a non-rotating black hole, the Schwarzschild radius is, you don't need to compute anything here. The important part is the proportionality. If mass increases, horizon size increases in the same proportion. So largest mass gives you largest horizon in a broad, meaningful sense. There is another meaning that sometimes sneaks in, biggest by gravitational influence. But gravitational influence depends on the environment. A black hole's sphere of influence can be harder to define and harder to measure, especially in huge galaxies where the stellar motions are affected by the galaxy's own mass distribution as well. So for a clean cosmic contest, mass is the standard. And because we can't put these giants on a scale, the next question becomes, how do we measure their masses at all? How astronomers weigh the biggest black holes. Measuring a supermassive black hole is like weighing a distant mountain by watching the motion of birds around it. You don't touch the mountain. You track the movement it causes. Different techniques work in different situations. Some are direct, but only possible nearby. Some work at huge distances but come with larger uncertainties. Watching stars move near a galaxy's center. If we can resolve stars in the central region, we can measure their velocities and sometimes their orbits. Fast motion close to the center implies a large compact mass. This is the method that gave us exquisite confidence in the mass of Sagittarius A, the black hole at the center of the Milky Way, because we can track individual stars over time. For the biggest black holes, the host galaxies are often far away. We can't track individual stars. Instead, we measure the combined light of many stars and infer average velocities, then build dynamical models to explain what mass distribution produces those motions. This is powerful, but modeling matters. The biggest galaxies have complicated structures. Their central regions can have cores, anisotropic orbits, and varying stellar populations. So stellar dynamics can give extremely important estimates, but they come with careful caveats. Watching gas move in central disks. Sometimes there is gas orbiting in the central region. Spectral lines shift as the gas moves toward or away from us, letting astronomers measure velocities. If the gas forms a relatively orderly disk, the mass estimate can be strong. But gas is not always orderly. It can be turbulent. It can be pushed by radiation. It can be disturbed by jets. So gas dynamics can be clean in some galaxies and messy in others. Timing light echoes in active galaxies. In active galactic nuclei, the brightness can vary. When the central region brightens, gas farther out responds with a delay, like an echo. That delay encodes a distance because light takes time to travel. This technique is called reverberation mapping. It turns variability into a ruler. Combine the inferred size of the emitting region with velocity information from spectral line widths, and you can estimate black hole mass. It's a beautiful method, but it relies on assumptions about geometry and calibration. Still, it is one of the most important ways we estimate masses for many active black holes. Estimating quasar masses from broad emission lines. For extremely distant quasars, astronomers often use single-epoch virial estimates. They measure the width of broad emission lines, which reflects the speed of gas in the broad line region. They use the quasar's luminosity to estimate the size of that region through empirical relations. Then they infer a mass. This method is a workhorse for high redshift quasars. It's why objects like TON 618 can be assigned masses at all. But it comes with significant systematic uncertainties, especially at the extreme ends. When someone says, this black hole is the biggest, and the evidence comes from quasar virial methods, it's wise to hear an implied phrase. From biggest within current estimates, biggest within uncertainties. Astronomy doesn't become weaker because it admits uncertainty. It becomes stronger. A calm note about largest known versus largest that exists. The universe contains far more black holes than we can catalog. We only know a black hole well if it leaves a measurable signature. The biggest black holes might be actively feeding and shining as quasars, or they might be quiet, embedded in giant galaxies, not announcing themselves loudly. Some could be hidden by dust. Some could be too distant for the level of detail we need. Some could be in phases of low activity where their surroundings are dim. So, largest known is a moving target. As surveys improve, as telescopes sharpen, as modeling gets better, the leaderboard can change. The record is not a crown welded to a single object forever. It's the best answer our data supports right now. And with that gentle realism in mind, let's meet the famous Titan that most often appears at the top of popular lists. 618, the most famous giant candidate. Titan 618 is a quasar, a brilliant, distant beacon powered by a supermassive black hole that is actively accreting matter. The mass estimates for TON 618 are commonly quoted in the range of tens of billions of solar masses, often around something like 60 to 70 billion solar masses, depending on the study and method. That number is so large it can feel like a fog. So let's translate it into pictures your mind can hold. The size of its event horizon, in solar system terms. Because the event horizon scale grows linearly with mass, a black hole of tens of billions of solar masses has an event horizon that, if placed where our Sun is, would extend far beyond the orbits of the outer planets. The diameter would be on the scale of thousands of astronomical units. An astronomical unit is the Earth-Sun distance. Thousands of those takes you out past Neptune and deep into the outer regions of what we casually call our solar system's neighborhood. That does not mean it would suck in planets from that distance like a vacuum. If you replace the Sun with a black hole of the same mass as the Sun, Earth's orbit would remain almost unchanged, because gravity at a distance depends on mass, not on whether the mass is a star or a black hole. But here, we're imagining replacing the Sun with a black hole that is tens of billions of solar masses. That would radically increase gravity in our region. Everything would change. The point of the comparison is not realism, it's scale. The horizon of such a black hole is not a tiny dot. It is a region so large you can meaningfully compare it to planetary distances. Why TON 618 shines. A black hole itself does not glow. A quasar glows because matter outside the horizon is falling inward. As gas spirals in, it forms an accretion disk. Friction and turbulence heat the gas. Magnetic fields twist and tangle. Energy is released as radiation, sometimes across the whole electromagnetic spectrum. A quasar can outshine the combined starlight of its host galaxy. It's not because the black hole is a lamp, it's because gravity is an engine. Gravity converts potential energy into heat and light as matter falls toward the horizon. TON 618 is famous because it is extraordinarily luminous and extraordinarily distant, implying we are seeing a powerful feeding phase in the early universe. But that also means its mass is often estimated with methods that, while sophisticated, are indirect. Which brings us to a gentle and important point: why the biggest black holes are hard to weigh precisely. If you were measuring something small in your hand, you could repeat the measurement 1,000 times. You could check it with multiple tools. For a black hole billions of light years away, you cannot. You rely on light arriving at a telescope. You rely on models relating observed properties to mass. You rely on calibration from closer systems. You rely on assumptions that are reasonable but not perfectly provable for each individual object. So the mass estimate for a distant quasar like TON 618 comes with a range. Different emission lines can give slightly different results. Orientation can matter. The structure of the broadline region can matter. The calibration of the radius-luminosity relation can matter. This doesn't mean the number is meaningless. It means it is an estimate, not a direct weighing. If TON 618 is estimated at around tens of billions of solar masses, it is certainly a giant. Whether it is the single largest known object can depend on which studies you prioritize and how you treat uncertainties. And there are other contenders. Some are quasars. Some are central galaxies in clusters. Some are debated. Some are more secure. The largest category is not a single throne. It's a small crowd at the top. The quiet cluster giants, black holes, in central elliptical galaxies. Many of the biggest black holes are expected to live in the centers of the most massive galaxies, and the most massive galaxies often live in the centers of galaxy clusters. A galaxy cluster is a gravitationally bound collection of hundreds or thousands of galaxies, embedded in a massive dark matter halo and filled with hot X-ray emitting gas. In the dense center of a cluster, the central galaxy can grow enormous by mergers. Galaxies fall in, they collide, they merge. Their stars redistribute. Their central black holes can eventually merge too. Over billions of years, the central galaxy becomes a giant elliptical with a complicated history. These central galaxies are where astronomers often suspect ultra-massive black holes, potentially in the tens of billions of solar masses range. Names that frequently appear in discussions include objects like NGC 4,889 inches, the Coma cluster, and certain galaxies in rich clusters, such as Abell 85. Different studies and models yield different mass estimates, and some claims have been revised over time. The key idea is not that every specific candidate is definitively the largest. The key idea is that cluster centers are plausible growth chambers for extremely massive black holes. M87, not the biggest, but the most vivid proof. The black hole in Messier 87 has a mass of about 6.5 billion solar masses. That is enormous, but not the top of the list. Yet M87 holds a special place in this story because the Event Horizon Telescope produced an image of its shadow. This tells us something profound. It tells us that supermassive black holes are not just inferred concepts. We can measure their gravitational lensing signatures at horizon scales. We can test general relativity in strong gravity. We can see the absence created by the horizon's geometry against glowing gas around it. If a black hole of 6.5 billion solar masses can be measured and imaged in this way, then the existence of black holes tens of billions of solar masses becomes less like a myth and more like a natural extension of the same physics. How black holes get that big? Growth without panic. Now we step into a question that feels like a quiet puzzle. How do you build a black hole with tens of billions of solar masses? Black holes grow by accretion and mergers. Accretion is the steady process of feeding, Mergers are the episodic process of combining with other black holes after galaxies merge. Both are important. Accretion, the slow meal that can shine like a lighthouse. As matter falls inward, it forms an accretion disk. If it has angular momentum, the disk heats up, it radiates. In the most luminous systems, radiation pressure can push back on incoming gas. A classic concept that describes a balance between inward pull and outward radiation pressure is the Eddington limit. We don't need to dive deep into formulas tonight. We only need the calm principle. A black hole cannot always feed arbitrarily fast in a steady, luminous way, because the light generated by infalling matter can resist further infall. That tends to set a characteristic timescale for growth if the black hole is shining near its maximum efficient rate. But nature has ways to bend simplicity. Accretion can be messy. It can be clumpy. It can be obscured by dust. It can be super Eddington for short periods in certain geometries. It can be intermittent. So a black hole can sometimes grow faster than the simplest, steady picture suggests, especially in early cosmic environments where gas was abundant. Mergers, growing by combining histories. When galaxies merge, their central black holes can eventually form a binary. Over time, through interactions with stars and gas, and ultimately gravitational waves, the black holes can merge into a more massive black hole. This is a slow and complex process, and in some scenarios, black hole binaries can stall for long periods. But in rich environments with repeated mergers, the central black hole can steadily gain mass through combination. The biggest black holes are often found in the biggest merger histories. That's not coincidence. It's accounting. A black hole's mass is a memory of what its host galaxy experienced. The seed question, starting big or growing fast. To reach tens of billions of solar masses, you can start from a small seed and grow with long, efficient feeding and many mergers. Or a larger initial seed, possibly formed from direct collapse of massive gas clouds in the early universe, then grow from there. Astronomers still investigate the relative importance of different seed channels. The existence of very massive black holes early in cosmic history suggests that either seeds can be large or early feeding can be surprisingly effective, or both. This is one reason the biggest black holes are scientifically valuable. They pressure test our growth models. They keep theorists honest. They keep observations meaningful. A gentle correction. Bigger black holes can be less violent at the horizon. Here's a counterintuitive fact that often calms people. Tidal forces are what stretch objects, what popular culture calls spaghettification. Tidal forces near a black hole depend on how quickly gravity changes with distance. For very massive black holes, the event horizon is so large that the gradient of gravity at the horizon can be smaller than it is for a smaller black hole. So, in principle, you could cross the horizon of an ultramassive black hole without experiencing extreme tidal stretching right at that boundary. That does not mean it is safe. It means the danger is not a dramatic barrier. The danger is that once you are inside, the geometry of space-time makes escape impossible. The horizon is not a trapdoor you feel. It's a boundary in your future. And that's part of why black holes are fascinating. They are extreme physics with quiet local behavior at the edge, especially for the biggest ones. The difference between loud and quiet giants. Some of the largest black holes are seen as quasars. They are loud in light. They announce themselves across billions of light years. Others are quiet. They sit in the centers of massive galaxies with low accretion rates. They can be extremely massive and yet not shine brightly. In these cases, we find them by their gravitational influence, by stellar motions, by gas kinematics, sometimes by jets in radio waves, or by the cavities they carve in hot cluster gas visible in X-ray observations. The quiet giants may be more numerous than the loud ones. Because quasar phases are believed to be temporary, a black hole does not shine like a quasar forever. It goes through phases, feeding phases, quieter phases, bursts, dormancy. So the census of the largest black holes is influenced by what phase they happen to be in when we look. This is another reason largest known is not the same as largest that exists. The cosmic environment of the biggest black holes. If you want to find the largest black holes, you don't search randomly. You look where growth is most plausible. You look in massive galaxies. You look in cluster centers. You look in the most luminous quasars at high redshift. You look for signs of huge gravitational wells and enormous host structures. The biggest black holes tend to live where matter has been funneled inward for a long time, where the host galaxy has grown by mergers, where gas flows have been strong in the past, where the dark matter halo is large, where the galaxy sits in a dense node of the cosmic web. In that sense, ultramassive black holes are not isolated oddities. They are the peaks of a landscape shaped by cosmic structure formation. Gravity builds networks. Matter flows along filaments. Clusters form at nodes. Central galaxies grow large, and in their centers, black holes can become enormous. The biggest black holes are an extreme but natural outcome of hierarchical growth, making the scale feel real. Comparisons that don't shout. Numbers like 60 billion solar masses can bounce off the mind. So let's build a few calm scale anchors. The Milky Way's black hole versus the ultragiants. Sagittarius A times is about 4 million solar masses. That is supermassive by definition. But compared to a tens of billions solar mass black hole, Sagittarius A times is much smaller. The comparison is not meant to make our galaxy feel insignificant. It is meant to show how wide the category supermassive really is. Supermassive is not a single size. It's a range spanning thousands of times in mass. The mass of a small galaxy concentrated, a black hole with tens of billions of solar masses, has a mass comparable to the stellar mass of some small galaxies. It's like compressing a modest galaxy's worth of matter into a single gravitational object, not in size, because the horizon is still tiny compared to a galaxy, but in mass, in gravitational accounting. This is one reason these objects are so remarkable. They concentrate huge mass into a comparatively compact region, horizon size compared to familiar distances. For stellar mass black holes, the horizon is kilometers to tens of kilometers. For supermassive black holes like Sagittarius A, the horizon is on the scale of millions of kilometers. For ultramassive black holes, the horizon can be large enough that solar system comparisons become meaningful. Again, This is not to imply proximity, it's to give your mind a handle. The biggest black holes have horizons that can be described with the language of planetary distances, even though they live in distant galaxies. What we actually observe when we claim a largest black hole, it's easy to imagine astronomers seeing a black circle and measuring it, but that's not usually how it works. For the largest candidates, we typically observe a bright quasar spectrum with broad emission lines, a host galaxy with stellar velocity dispersion signatures, gas kinematics suggesting a strong central mass, radio jets and lobes indicating an active nucleus, X-ray cavities in cluster gas showing energy injection from a central engine, gravitational lensing patterns telling us about mass distributions indirectly related to the growth environment. Each observation is a piece of a puzzle, and then models connect the pieces. So when you hear a mass estimate like 60 billion solar masses, understand it as a carefully inferred value built from data and theory, not a casual guess, but also not a direct weighing on a scale. Why the record can change? Uncertainty at the top end. At the top end of any distribution, small changes matter. If one black hole is estimated at 60 billion solar masses and another at 40 billion, the ranking seems clear. But if the uncertainties are large, the ranges can overlap. And if new data revises one estimate upward or downward, the ranking can flip. This happens in astronomy. It is normal. It is healthy. The important thing is that multiple independent lines of evidence support the existence of black holes in the tens of billions category. The exact ordering may change. The existence of the class does not. That's the stable result. There are black holes so massive that they sit beyond the billion solar mass scale and into a rarer, more extreme realm. The question behind the question: why do we care? Why does it matter which black hole is the biggest? Not because we need a cosmic trophy, but because the biggest black holes constrain the physics of growth. They tell us how much matter can realistically be funneled into a galactic center, how feedback from jets and radiation shapes galaxies and clusters, how mergers and accretion histories unfold, how early structure formed, how quickly massive systems assembled after the Big Bang. The biggest black holes are boundary markers. They sit at the edge of what our models must explain. And boundary markers are precious in science. They are the places where new understanding often appears. A slow, detailed portrait of a quasar engine. Let's take a calm moment to imagine the environment of a truly enormous feeding black hole. At the center is the black hole. Around it is an accretion disk, hot and bright. The inner disk can be so hot it emits strongly in ultraviolet and X-rays. Farther out, cooler regions emit optical and infrared. Above and below the disk, magnetic fields can channel material into jets that shoot outward at relativistic speeds. Not always, but often, especially in radio-loud systems. Surrounding the disk is a region of fast-moving gas clouds that produce broad emission lines. Their line widths reflect their velocities. Their velocities reflect the gravitational potential. And by connecting those measurements to the size of the region estimated through luminosity relations or reverberation mapping, astronomers infer mass. Farther out still is dust, forming a torus-like structure in some unification models, absorbing and re-emitting radiation in infrared. Beyond that is the host galaxy, stars, gas, dark matter, mergers, inflows, outflows, and beyond the host galaxy may be a dense cosmic neighborhood where interactions and gas supply are more common. A quasar is not a single object. It's an ecosystem, a temporary but powerful phase in the life of a galaxy. And the biggest black holes, when they are active, are among the most luminous ecosystems in the universe. They are visible across vast distances because they are converting gravitational energy into light with extraordinary efficiency. The quietest way to think about the biggest. Now let's come back to a peaceful framing. A black hole does not have ambition. It does not try to become the biggest. It grows if it is fed. It grows if it merges. It grows as gravity guides matter inward. The biggest black holes are not monsters. They are bookkeeping outcomes. They are what happens when a galaxy experiences a long history of mergers and inflows. They are what happens when the cosmic web delivers matter to a dense node over billions of years. They are what happens when physics repeats itself on very large scales. And because the rules are consistent, the result is consistent. Mass sets the horizon scale. Spin shapes the surrounding spacetime. Accretion disks radiate. Jets can form. Galaxies co-evolve with their central black holes. Nothing supernatural, just nature, given time. Could there be something even bigger than TON 618? It's possible. The observable universe is vast. Our surveys are incomplete. Many quasars remain to be studied in detail. Many cluster central galaxies remain to be modeled with improved data. Some black holes could be quiet, not actively accreting, making them harder to measure. Some could be obscured. Some could be in systems where the central dynamics are complicated, so TON 618 may not be the absolute largest that exists. But it remains one of the most widely cited and compelling candidates for the most massive known black hole, based on current data and commonly referenced estimates. And the existence of multiple competitors in the tens of billions range suggests that the universe's upper end is populated, not singular, a small set of extreme objects, rare but real, a gentle myth-busting interlude, black holes and sucking. Because this comes up often and it can disturb people's sleep. Black holes do not suck more than any other object with the same mass. If the sun suddenly became a black hole with the sun's mass, Earth would not spiral in. Earth would keep orbiting. What would change is that the sun would no longer shine. The solar system would become cold and dark over time. The orbital mechanics would remain almost the same. Black holes only become a threat if you get very close, just like any massive object. The difference is that with a black hole, very close includes a boundary beyond which escape is impossible. But from a safe distance, gravity is gravity. So the biggest black holes are not cosmic vacuum cleaners sweeping galaxies into their mouths. They are central masses around which galaxies organize, while stars orbit at huge distances, mostly unaffected in the day-to-day. A galaxy is mostly empty space. Even in mergers, stars rarely collide. The chaos of a merger is gravitational, not like billiard balls smashing. This calmer reality is closer to the truth, and truth tends to be soothing. Jets, feedback, and why giant black holes can shape clusters. One of the most powerful ways a supermassive black hole influences its environment is through jets and feedback. When a black hole accretes, some of the infalling energy can be redirected into collimated jets. These jets can inflate bubbles in the hot gas of a galaxy cluster. X-ray observations sometimes show cavities regions with less X-ray emission, where the hot gas has been pushed aside by jet activity. This is feedback in action. The black hole is small compared to the galaxy and tiny compared to the cluster. Yet it can inject enough energy to influence gas cooling, star formation, and the thermodynamic history of the cluster core. This is one reason black holes matter far beyond their horizon size. Their influence is not because they reach out gravitationally in some exotic way. Their influence is because accretion can convert gravitational energy into radiation and mechanical power, which interacts with surrounding matter. In the largest galaxies and cluster centers, feedback can become a key part of the ecosystem. It can prevent gas from cooling too quickly. It can regulate the growth of stars. It can shape the long-term evolution of the central galaxy. So the largest black holes are not just endpoints. They are active participants in cosmic structure. The early universe problem: giant black holes appearing too soon. Some of the most intriguing black holes are those found very early in cosmic history. Quasars at high redshift show that black holes of 1 billion solar masses existed when the universe was less than 1 billion years old. That is already challenging. It implies rapid growth. It implies large seeds, efficient accretion, or both. The ultramassive tens of billions category tends to be discussed more often at somewhat later cosmic times, where there has been more time to grow. But the general theme remains. Very large black holes place strong constraints on how quickly matter can assemble and funnel into centers. They encourage research into direct collapse black hole seeds, dense early gas inflows, super Eddington accretion episodes, the role of mergers in early structure formation, the interplay of feedback and growth. So even if tonight's focus is the biggest, the scientific importance is that these objects illuminate the entire growth history across cosmic time, a slow-scale ladder told as a drifting thought. If your mind likes ladders, here is a quiet one, not with numbers, but with imagery. Imagine a small black hole made from a collapsed star. Its horizon is tiny on human scales. Now imagine Sagittarius A times in the Milky Way, a supermassive black hole, millions of solar masses. Its horizon scale is large enough to compare to the size of stellar orbits near the center. Now imagine M87's black hole, billions of solar masses. Its environment produces a jet that reaches far into intergalactic space. Now imagine the ultra-massive candidates, tens of billions of solar masses. Their horizons, in diameter, become comparable to distances that sound like the outer solar system. And then imagine the universe continuing to evolve. Galaxies merging, clusters growing, matter flowing along filaments, black holes gradually gaining mass. The ladder doesn't end because physics changes. It ends because the universe has only had so much time, and the environment provides only so much fuel. That's the quiet ceiling. Not a rule that forbids larger black holes, a practical ceiling set by cosmic history. Closing. The biggest black hole has a peaceful landmark. As you drift towards sleep, you can let the idea of the biggest black holes become less like a headline and more like a landmark on a map. Somewhere out there, very far away, are black holes with masses tens of billions of times the Sunday. They sit in the hearts of immense galaxies or shine as distant quasars. They are not hunting. They are not moving toward us. They are simply regions where gravity has written itself into a deep curve of space-time. Their horizons are vast compared to ordinary black holes. And yet, compared to the universe, they are still small points. Powerful, yes, but not dominant over everything. Just extreme outcomes of patient laws. If TON 618 is the largest known by common estimates, it holds that title with an important asterisk. Largest known with current methods. Largest known with current data. Largest known within uncertainty. Science does not fear the asterisk. Science lives by it. And the comforting part is that, asterisk or not, the universe clearly creates giants. Giants formed not by magic, but by time, by gravity, by the slow gathering of matter through cosmic history. So you can let your mind rest on that thought. A universe where even the biggest things are made by simple rules. A universe that doesn't need to rush. A universe that builds its largest black holes the way it builds everything else. Patiently, quietly, one orbit, one merger, one slow inflow at a time. And while those giants exist far away, your own world tonight is small, safe, and still. Just breathing, just resting, while the universe continues its calm work in the dark. Sweet dreams.